These interfaces impact things like air quality, they impact water quality, they can actually impact climate because particles nucleate clouds. They impact the ozone layer. Okay, so there are a wide range of environmental interfaces and they have very important impacts on health.
Hello and welcome to the Pittcon podcast. Today we sit down with Vicki Grassian to discuss using spectroscopy as a tool to understand the chemistry of environmental interfaces. Thank you so much for joining me here today, Vicki. Please could you just start off by introducing yourself and giving us a brief overview of your current research activities?
Okay, so my name is Vicki Grassian. I'm currently a distinguished professor at the University of California, San Diego. I started my career at the University at Albany, where I got my bachelor's degree, and then my master's degree at Rensselaer Polytech Institute, and then I went to UC Berkeley for my PhD.
And what initially sparked your interest in your field of study, and how has this passion evolved over your career?
So the field of study of environmental interfaces, the chemistry and impacts of environmental interfaces, that's an area I have been in since the transition between assistant and associate professor. My background is in surface science and surface chemistry, and just at that time I began to really become interested in the environment, in the atmosphere, and trying to understand how interfaces played a role in the chemistry of the atmosphere and the environment.
And could you explain how the chemistry of environmental interfaces impacts our everyday lives? And why is it so crucial for the general public to know more about this?
So first of all, there are a wide range of environmental interfaces. There's particulate matter in air and the surface of those particles in air. There's minerals in groundwater and the interface between those solid minerals and the water, aqueous water system above it. These interfaces impact things like air quality, they impact water quality, they can actually impact climate because particles nucleate clouds. They impact the ozone layer. Okay, so there are a wide range of environmental interfaces and they have very important impacts on health. And when I say health, I mean human health, ecosystem health, as well as planetary health. So I think it's important for people to understand sort of the implications of these interfaces and how they play a role in health.
And are there any misconceptions that people have about environmental interfaces?
I think people don't really think about them very much. I mean, you can look out at the ocean. We're here in San Diego. You have the Pacific Ocean. There's the air-water interface. Sometimes the Pacific Ocean gets polluted. So you'll see signs, don't go swimming in that water. But actually, there are other things that are going on. There's a lot of exchange between the water and the air. And so I don't think people think about it. We're now starting to think about that here in San Diego because we've had some situations where we've had some runoff from contaminated waters in the Pacific Ocean. So people are just starting to think about it and actually really wanting to have changes so that the air they breathe is of good quality and the water is also of good quality.
And what are some of the biggest challenges that you faced in researching the chemistry of environmental interfaces? And how has your work helped to address them?
So some of the biggest challenges had to deal with getting people to realize the importance of the field and the approach that we were taking. My background in surface science and surface chemistry was done in ultra-high vacuum, on pristine single crystal surfaces, sometimes addressing issues related to heterogeneous catalysis. I wanted to take that information and look at the more complex environmental systems that we were interested in, the environmental surfaces and interfaces we were interested in. And so people had some doubts that that could not be done. And what were those doubts? How did they manifest themselves in being a challenge? Well, for for example, I would submit a paper, it would be reviewed, I'd revise the paper, it would be reviewed again, I revised the paper, it would be reviewed again. People would say things like, I wouldn't write that paper in that way, but it was our paper, and we did work through that. We had the tenacity, if you will, to keep on going and work through that, and then it would be published. In terms of proposals, people would suggest, oh, this is too complicated, you wouldn't be able to understand anything. And it was complicated, but we were able to design the experiments in such a way that we can learn quite a bit. And so we took up the challenge of it being complicated or people having their doubts and really forging a way in a new area of research.
It must have been quite satisfying as well to be able to have success in that way after having, so many pushbacks, even from the research community.
Absolutely.
Yeah.
Absolutely. So yeah, it's been very gratifying.
Mm-hmm. Mm-hmm. And within your work of atmospheric aerosols, what are some of the most significant findings that you've encountered in this area? And how can they help to contribute to our understanding of environmental chemistry?
So in our work on atmospheric aerosols, we really have helped we've really developed a conceptual framework for understanding the chemistry of different types of aerosols, such as mineral dust aerosol. There's a lot of dust in the atmosphere. Planet Earth has a lot of desert regions, arid regions, which could become even more due to climate change. The dust gets in the atmosphere, it affects, and it's transported many miles away. And so it really can impact the particulate matter loading in the atmosphere. We've looked at how reactions on the surface of those particles can change the composition of the particles. We've actually shown in one case, when you have calcium carbonate, it's a very important mineral. It's involved in even regulating CO2 in the atmosphere, how it can react and with nitrogen oxides to form calcium nitrate. Okay, so why is that important? Calcium carbonate's a solid, calcium nitrate's actually a liquid. It takes up water, it becomes an aqueous particle. So we have phase transformation, solid to liquid particle. That particle can now easily nucleate aqueous clouds. And so there's a lot of implications to the chemistry. We've looked at iron-containing mineral dust particles and the amount of soluble iron that's available, and that's known to be, soluble iron is bioavailable, and so knowing that is important. We've done research on just looking at the spectral characteristics of mineral dust aerosol in the infrared. People are using that for remote sensing. NASA now has a big program called EMIT, where they're determining the mineralogy of the Earth system to better understand mineral dust aerosol. And I think they're going to be using some of our data to interpret some of the measurements that they're making now.
Mm-hmm. That's really fascinating. I can imagine as well, with some of these particles then, for want of a better way, going off into clouds, it probably has implications for precipitation and weather systems as well.
Absolutely. That has been shown. Another type of aerosol that we studied quite a bit is sea spray aerosol. So particles coming from the ocean, the aerosols coming from the ocean. We've been able to use different methods to determine more about its composition, how it nucleates ice clouds. So mineral dust and sea spray aerosols combined are the largest mass of aerosol in the Earth system.
Oh, wow. Kind of moving specifically onto your career. So you've developed a variety of spectroscopic techniques. Could you tell us a little bit more about these different techniques and which of these technologies do you believe to be the most pivotal in advancing your field?
So the way we have approached these studies of environmental interfaces and atmospheric aerosols in particular has been using vibrational spectroscopy as a probe, actually as an in situ probe of the chemistry. So we do a lot of laboratory experiments to better understand the complexity of the Earth's atmosphere, trying to take the components that we think are most important to understanding that chemistry. So we do a lot of experiments as a function of relative humidity. There's a lot of water vapor in the atmosphere, how that plays a role in the chemistry. And so vibrational spectroscopy is one infrared spectroscopy. We've used simple transmission IR spectroscopy, attenuated total reflection IR spectroscopy, atomic force microscopy coupled to infrared spectroscopy.
It's like a bingo card.
Optical photothermal infrared spectroscopy, plus Raman. We've been doing some Raman spectroscopy, which are different selection rules. All of those taken together, depending on the problem we're trying to understand, depending on the length scale that we're looking at, has given us information on various chemical processes, as well as even climate relevant properties in ways that has been very helpful. You know, if you think about vibrational spectroscopy, it probes individual molecules and moieties, ions, and you have these spectral characteristics that are well known, but you put that molecule or ion in these different environments and their vibrational spectra change some. And by changing some, it tells us something about the local, I talk about the bigger environment, but this local molecular environment that actually plays a role in its reactivity, how it behaves, absorbs light, even solar radiation. And so we've utilized these techniques, a variety of them under this umbrella of vibrational spectroscopy, as a way to probe these environmental interfaces.
Mm-hmm. And have you noticed there's been a bit more of an uptake in also combining these different spectroscopies with modeling or even machine learning technologies?
Yeah, that's a really good question. So we have, over the course of years, worked with theorists to better understand and interpret some of our data. We've also worked with atmospheric chemistry modelers to put some of the data that we have into those models. We work with people who do field measurements so they can better understand what's going on in the atmosphere, in the field. And so in terms of the machine learning, that's coming into everybody's research, AI. And so, yes, it's also coming into our research, whether it's through our modeling collaborations or how we're even thinking about doing our experiments.
So in your Pittsburgh Spectroscopy Award address, you're going to be focusing on some of these spectroscopies as a probe for environmental interfaces. Could you give us a bit of a preview of how spectroscopy uniquely contributes to understanding these complex systems, particularly the ones you'll be discussing in your address?
Yeah, so we did a study recently looking at sulfur oxidation chemistry, which has been well known for decades. But the thing is that people have been doing this chemistry, when they do it in the laboratory, in what we call bulk aqueous phase, like in a beaker. Mm-hmm. What we've been doing and following with our spectroscopic probes is looking at it in much smaller micron size, more relevant sizes to the atmosphere, and really seeing how the interface plays a role in that chemistry. So we have been doing confocal Raman spectroscopy of aqueous aerosols from 1 to 2 to 5 to 100 microns in size, and seeing how size affects the rates of these reactions. And so now we have to add into these models interfacial chemistry. I showed another example of a very different environmental interface in my talk at the meeting. I showed a lot of unpublished data. Okay. I wanted to jazz it up. I did talk about some of the older things we did, but I wanted to jazz it up. We've been interested most recently in environmental DNA. So this is DNA in the environment. It's not in a cell. It's not in an organism. The cell gets lysis, and you have lysis, and so DNA gets into the aquatic environment. And there's a hypothesis out there that if DNA sticks to surfaces in the environment, it will protect it from undergoing any degradation. So when I think about that problem, I think about there are a myriad of surfaces in the environment. Are they going to all behave like that? And so we just started some work looking at DNA adsorbed onto mineral oxide surfaces, and determining whether its structure stays intact. The B form is the typical form. It has a certain handedness, it has a certain structure. And what we've learned so far is that it really depends on the mineral, what DNA is doing, what its structure is on the surface, and we use spectroscopy as a probe of that. And so that's been a recent exciting result of ours that we really want to get in the literature soon, and we're just writing up some of our initial papers. And once you do, that's a big topic, and once you do one thing, there's then 100 other things that you want to do. And what's satisfying from my perspective is one of my first papers that I ever wrote was on DNA. And that was many, many, many years ago. So it's coming full circle, and we're looking at DNA and its structure once again.
Wow, that's a really fascinating topic. I have a genetic background, so to hear that there is this interaction that is actually preventing degradation is just fascinating.
Well, on one surface it does prevent degradation. On another surface it actually causes degradation and the breaking of the double strand to single strands. And once you're a single strand, you can undergo degradation faster than the double strand. That's well known. So I've started to have conversations with people with your background and others that make me realize how interesting, even more interesting than I'm thinking this research is, and how much more we can be doing.
Oh, well, I look forward to seeing the papers when they come out. So, speaking again specifically to your presence here at Pittcon, so you have received the Pittsburgh Spectroscopy Award, which is a significant achievement. How does it feel to be recognised for this award, and what does it mean to you personally to have received it?
So at the award symposium, so that did happen yesterday, and they were, when they introduced me, it was really so gratifying. They read from the nomination letter, talked about my work in terms of these accolades and these accomplishments, and I was just sitting there as they were introducing me, and I was beaming. When I stood up to give my talk, I had the biggest, broadest smile on my face, like, a 16-year-old being given the keys to a car or something. I was just ecstatic. I felt so good. I'm going to ride this for a little while. I'm going to ride this for weeks, I hope, maybe months. It was very personally very satisfying because, we put a lot of work into this. And so personally to be gratified in that way, to hear those words said about me was just wonderful. Professionally, I would say it was also great, and it really is a testament to the students and the postdocs that I've worked with over the years. A lot of the time, as the PI of the laboratory, I'm talking to my students, but they're the ones going in there, making everything work, collecting those spectra that we get to interpret. And so it's really just professionally very satisfying to hear that your peers have thought so highly of you and your research group's work over the years. And so it couldn't feel any better.
Pittcon Perspectives, unforgettable Pittcon moments from the experts.
So again, building on your presence here at Pittcon, in your view, how does a conference like Pittcon contribute to the advancement of science, particularly in the fields related to chemistry and spectroscopy?
So Pittcon is a very important meeting. It's important, and it has been for many years, 75 years. It's really the forefront of analytical chemistry, analytical techniques. And so if you want to know what's new, you come to Pittcon. You go to the expo, the exposition, to see all the latest tools. I know that people in industry, they prep for Pittcon. They want to show everybody what's new, the latest software, whatever. So Pittcon is a very important meeting. Besides the exposition, there's also the excellent technical talks. So it really brings in industry, academics, people from national labs, together to see what's new in analytical chemistry and analytical instrumentation. There's no other meeting like it.
Mm-hmm. Mm-hmm. And you've mentioned that it's the 75th anniversary of Pittcon this year. Could you share your first memory or your first experience of attending this conference and how it's impacted your view on both your own scientific community, but just the community as a whole as well?
So I have several memories of Pittcon over the years. My first is when I was a brand new assistant professor. I didn't mention this, but I started at the University of Iowa and spent 20 plus years before I moved to UC San Diego. And I remember Pittcon was in Chicago one year. I had just started, I was 2 months in as an assistant professor, and I drove to Chicago because I wanted to see the newest instrumentation and everything that was going on at Pittcon and meeting people at Pittcon. And I remember being so intimidated by everything, including the titans in the field at the time. And so that's my first memory of Pittcon. Then I remember being an invited speaker at Pittcon, and they treat their invited speakers very well. So I had a great time as an invited speaker. Then later on, I actually did co-chair a symposium here at Pittcon, and that also happened in Chicago. I remember that very, very well. And it was a really wonderful symposium. And after the symposium, someone came up to me and handed me their CV and said, I'm wondering if you're taking any postdocs. I'm finishing my graduate studies. And I wasn't necessarily looking for a postdoc, but I looked over the CV. I had an interview with that person, and I ended up working with one of the smartest people I ever met from that, because he was quite a great postdoc and really brilliant. He might even be here at Pittcon. I haven't bumped into him yet because he works for Thermo Fisher, but that was really a wonderful thing that happened. We ran a symposium. I met a future postdoc who was brilliant, and we ended up writing some really, really nice papers. And then we come to hear the 75th anniversary of the Pittsburgh conference, the Pittcon, and all that it has been as the awardee of the Spectroscopy Award. That is so amazing for me as a person who's been going to Pittcon now for 30 years.
It sounds like Pittcon's just become a really big part of, your career, really.
And I think a lot of people's. And I think there's a lot of energy at Pittcon, and I think you've seen that here at the 75th anniversary.